So let's take a closer look at how you can charge up a parallel plate capacitor. All right, so let's connect a parallel plate capacitor to some battery with positive and negative terminals. All right, let me draw something like this. And that's my hypothetical capacitor. I'll draw one wire going to the top plate from the positive terminal and another wire going to the bottom plate from the negative terminal of the battery. Remember, this battery has some potential difference V, right, inherent in the battery, right? It takes the stored chemical energy and converts it to electrical energy, okay? So when we connect this parallel plate capacitor, which is composed of, two conductors separated by a distance d, okay? When this happens, let's take a look at what the charges are actually doing in these wires, okay? So when we connect it from the negative terminal to the bottom plate, electrons are effectively being repelled by the negative terminal here. So there's a net movement of electrons onto the bottom plate, giving this a total net negative charge. Okay. At the same time, on the top plate, which is connected to the positive terminal, that effectively makes positive charges be repelled from the plus terminal, right? Whoops, it goes like that. And then positive charges go along the top wire and then are accumulated and built up on the top plate. So eventually, this top plate of the capacitor gets a net positive charge. As this occurs, right, there creates a stronger and stronger electric field between the top and bottom plates, right? So in blue, there's a field going from top to bottom, right? Some electric field. When they're unconnected to this battery, right, when there's no net or excess charge on these plates, the potential is zero, right, because there's no electric field. They have no excess charge. But now, as they're charging, the magnitude of both this field and the potential between the plates increases up until a point where the potential of the capacitor, right, in between these plates is the same as the potential of the battery. That means that the potential for this top plate is the same as the potential at this positive terminal. So the delta V between those 2 points is zero. Thus, there will not be an electric field in the wire pushing these charged particles away, right, or moving those positive particles. Similarly, for the bottom plate, the bottom, the negative terminal there is at the same potential as the bottom plate here. So there's a net electric field of zero on the bottom, and so there's no movement for electrons in the bottom wire. So overall, in this electric circuit, there's an electric field of zero everywhere except in between the plates. And that's where we want to look when calculating what the capacitance is for this type of capacitor. So let me redraw this a little differently here. I'm going to draw the plates of some thickness separated by that distance d. Okay, so let's do this. That's separation distance d. The top plate will go plus, 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 plus. Negative plate, negative. That electric field still going from top to bottom. Okay. And remembering that the capacitance is basically the ratio between the amount of charge that's able to be stored in this conductor, it's a ratio of that to the potential difference across them. So in other words, the capacitance is equal to Q over delta V. Okay. You can think of this another way as, let's see, Q equals C delta V, where the amount of charge and the electric potential between these plates are directly related to one another, right? In the case of the circuit, it depends on the voltage of the battery, but the charge and the voltage are directly proportional, and that proportionality constant is C, right? For right now, it's unknown. We don't know exactly what it is for a parallel plate capacitor. That's what we want to find out in this video, okay? So for a given battery or for a given voltage source, right there, this parallel plate configuration, right, these two conductors can hold a certain amount of charge Q. Thus, that creates a certain potential difference, delta V, between them. So for all parallel plate capacitors, it will have the same value, or not the same value, but the same general expression for C, the capacitance. So let's see how we calculate that. So what we need to do is to independently calculate Q and delta V, right? Independently. So Q, we can use Gauss's law. And delta V, we can use the relationship between the electric field and the path length. I don't know if that necessarily has a name. So we can use that, okay? So Gauss's law. Well, what's that? Well, we need to create a Gaussian surface in this parallel plate configuration on the right in order to try and estimate the charge. So let's create that Gaussian surface such that it's passing through one of the plates physically and passing through the electric field in between them. Right, so our Gaussian surface, let's write this up here, is that dotted line. Okay, and so now on the bottom side of that surface, our dA vector, or our area vector, can point down. Okay. And we can write Gauss's law in this form. Q equals epsilon naught, or rather the charge enclosed, right, equals epsilon naught times the closed integral of that electric field dotted with dA. Okay. And let's take a look at what this turns out to be. Epsilon naught is constant. The electric field, once these conductors and once this capacitor is fully charged, the electric field is constant. So we can pull that outside the integral. What's the angle in between E and dA? Well, it's 0. So let's write it like this. Closed integral of dA is simply a, but the cosine is of 0. And so now, what's the area? Well, let's just call that dA, right? These capacitors have some cross-sectional area of A. So thus, we have epsilon naught E times A. And that's for our Q. Okay, now let's do the delta V, or the voltage between the top and bottom plates. So let's go delta V, same thing as final minus initial voltage, equals negative E dot ds, right? The electric field dotted with some path length, and we are free to choose that path. And thankfully so, let's go initial to final, okay? So that negative sign, we don't necessarily want that in our capacitance expression, right? This constant should be a positive number. So let's try and find a way to get rid of that negative sign. The way we do that is to invert the integral. Okay, so the voltage difference, the voltage from the final position minus the voltage from the initial position, well, if we go from top down, let's go like that. That is our ds, if you will, right? Well, we can flip this around. If we do that, that makes the integral, multiply by a -1, right? It makes a positive in this case. So if we flip that, we have final to initial. And now it's the same thing of E dot ds, okay? And that can be written, right? Our final plate is negative to positive, in other words. The angle in between the electric field and ds in this case, well, E is down and ds also down, so the angle's 0. So thus the magnitude of E, I guess I could bring that outside of the integral since again it's constant. What's the integral of ds? Well, that's pretty easy. Integral from negative to positive of ds is just simply d in this case, right? That's the separation distance, and so that's our delta v. And by convention, in this chapter and onward, we'll really see the potential difference written as just v, okay, for whatever reason. They kind of leave out and truncate the delta and just assume that v is a change, okay? So now let's plug in this and this into our capacitance, and we get epsilon naught times the electric field times the area, right, the cross-sectional area, divided by electric field times d. And so we get the expression epsilon naught times A over D for the capacitance of a parallel plate capacitor. So taking a look at this expression now, and this again applies for all parallel plate capacitors, right? If we increase the area of these plates, we simply make them bigger. What happens to the capacitance? It increases. In other words, it holds more charge, which should make sense, right? There's more room, effectively, to hold more charges on each plate. If we increase the distance between the plates, so they get further apart, it's harder for that charge to be transferred, right? Or rather, the potential, in other words, is decreasing, right? So the capacitance value is decreasing as well. Okay, it's harder to release that charge once the capacitors are discharged, right? It should be made clear that since there's no electric field and when they're fully charged, right, there's no electric field in the wires, there's just a field in between. However, there's no physical movement of charges. There's a field, but there's no movement of these charges between the plates. It's when the capacitor is discharged, that's when the charges move, and we get a release of electric potential energy, right? And a release of current that we'll see in a couple sections, okay? So in essence, this is the expression for the capacitance of any parallel plate capacitor.